Within this code excerpt, multiple libraries and modules crucial for data processing and machine learning assignments are imported. Let's delve into the specifics to begin with 1. The math module equips us with mathematical functions conforming to the C standard. Next up 2. numpy, shortened as NIP, serves as a Python framework tailored for handling arrays and matrices. Furthermore, it boasts an extensive array of sophisticated mathematical functions primed for operation on these arrays. 3. Pandas, denoted as PT, stands out as a robust data manipulation tool constructed atop numpy. It streamlines the process of working with structured data, positioning it as a swift, straightforward, and expressive solution. 4. Activated through Pandas Data Reader as web, Pandas Data Reader empowers the creation of a data frame using data stored from diverse online platforms like Google Finance and the World Bank. 5. Within scikit-learn Preprocessing, the min-max scalar function shines as a go-to for scaling numerical data within a specified range. It stands as a prevalent choice in machine learning models for normalizing features. 6. As for Keras models, sequential emerges as a versatile Keras model enabling users to construct deep learning models methodically, layer by layer. This model represents a linear sequence of interconnected layers. 7. Delving into Keras layers, we encounter dense and Wilson layers. Dense emerges as a standard fully connected neural network layer. Meanwhile, Wilson long short-term memory emerges as a distinctive type of recurrent neural network layer cherished for its ability to grasp prolonged dependencies. 8. Last but not least, matplotlib, pplot as pulp commands attention as a plotting library exceeding boundaries in rendering static, animated, and interactive visual representations within Python. Pplot encapsulates an array of functions geared toward establishing figures and plots seamlessly. Through the integration of these libraries, a myriad of machine learning tasks comes within reach, spanning data preprocessing, modeling, training, and assessment. These libraries not only furnish a diverse range of functions but also set the stage for efficient and effective data handling practices. In this line of code, a variable called ticker is created and initialized with the value AMZN, a common shorthand for the trading symbol of Amazon, Inc. This piece of code is a standard practice in programming for holding a particular value, like Amazon stock symbol, for easy reference without the need to retype AMZN multiple times. By storing it in a variable, the code becomes more concise, readable, and simpler to manage. It is a widely adopted approach in finance, data analysis, and various other fields where a distinct label, such as a stock symbol, is necessary to be preserved and operated within the code. Within this code snippet, a string value TSLA is being assigned to a variable named ticker. In the realm of programming, variables play a crucial role in storing and handling data. In this particular instance, ticker serves as a representation of the stock ticker symbol TSLA affiliated with Tesla, Inc. This variable is accessible and open to modifications across the codebase to reference the designated value. The act of assigning values to variables, as seen here, is fundamental in coding, facilitating streamlined reuse and alteration of data within the program's framework. This practice significantly contributes to enhancing code readability, manageability, and overall efficiency. The following line of code establishes a variable dubbed as ticker and sets its value as Uber. In this scenario, Uber is most probably symbolizing a stock symbol employed to distinguish a specific company traded on the stock market. Saving the stock symbol within a variable streamlines the process of mentioning and managing this value across the codebase. Sans the necessity to repetitively input Uber, such a practice can elevate code comprehension, sustainability, and adaptability. In the provided code snippet, a variable named ticker is instantiated and set to TSLA. This value TSLA typically stands for stock ticker linked to Tesla Inc., denoting its presence on the stock market. Stock ticker symbols function as concise identifiers for publicly traded assets on designated market platforms. By utilizing variables such as ticker, we can conveniently retain and access this data within our code, enhancing the management of information associated with a particular stock symbol across our program. Utilizing the data reader function from the Pandas Data Reader data module, the script fetches financial data, including stock prices, from Yahoo Finance for a designated stock or index specified by ticker. The data retrieval spans from January 1, 2015 to May 24, 2020, this script proves valuable by providing users with convenient access to historical financial data for diverse purposes like analysis, visualization, or any application that relies on historical stock prices. By programmatically obtaining this data, users can streamline the process of accumulating extensive financial data for analysis and research, ultimately saving time and effort compared to manual data collection. In Python, utilizing the pandas library allows you to access a data frame's dimensions using the def shape code. This code yields a tuple that denotes the data frame's row and column count. The initial value in the tuple signifies the row quantity, whereas the subsequent value denotes the column quantity. Employing this code proves to be beneficial for swiftly gauging your data frame size prior to engaging in subsequent operations or analyses. Grasping a data frame's dimensions aids in comprehending your data's layout, thereby influencing the way you manipulate and analyze the data. This snippet of code alters the plot style generated in Python scripts or Jupyter notebooks utilizing matplotlib. Here, the chosen style is dark background, offering a dark color scheme to the plot. Employing this code excerpt proves advantageous when aiming to tailor the look of your plots for enhanced visual appeal or to match a particular theme consistently. Adjusting the style enhances both readability and aesthetics of the plots created with matplotlib, a critical aspect for data visualization and presentation endeavors. This snippet of code serves the purpose of generating a line plot that illustrates the opening price fluctuations of a particular stock across a timeline. Let's delve into the specific functionalities of each segment. 1. By executing pult. Figure fixes a 16:8. The dimensions of the plot are defined as 16 inches in width and 8 inches in height. 2. The line pult. Tively opening price assigns the title opening price to the plot. 3. Through pult. Plot open. Data from the open column within the data frame diff is graphed, portraying the stock's opening prices on the y-axis. 4. The code pult. Clibble date. Font size 18 designates date as the c-axis label, adjusting the font size to 18. 5. Pult. Label open price cust. Font size 18 is used to set open price cust as the label for the y-axis, also with a font size of 18. 6. Finally, pult show is called to exhibit the plot visually. This code snippet is a valuable tool for comprehending the patterns and trends in a stock's opening price over time. It aids in identifying correlations within the data, facilitating informed investment decisions and financial analysis. By visualizing the data in this manner, it becomes more accessible to interpret and share key insights effectively. This script carries out several tasks. It filters out the open column from the data frame diff. It then transforms the extracted column into a numpy array. Lastly, it determines the length of the training data, which corresponds to 80 of the total data length, and utilizes the math.il function to round it up to the nearest whole number. The purpose of this script is to prepare the data for training a machine learning model. In this scenario, the script likely establishes the training dataset size, typically set at 80 of the whole dataset. This segmentation enables us to allocate one portion of the data for training the model and reserve the remainder for testing and evaluating the model's performance. This partitioning strategy is widely employed in machine learning to gauge the generalizability of a model to new, unseen data. The provided code snippet demonstrates the implementation of min-max scaling for feature scaling on a dataset. In this process, the min-max scaler is utilized to adjust the dataset values within a predefined range, usually between 0 and 1. This scaling technique holds significance as it normalizes the data within a consistent range, aiding in standardizing the independent variables ranges and ensuring each feature holds equal weight in machine learning models' similarity evaluations. By using the fit-transform method, the scaling operation is applied to the dataset, and the adjusted data values are returned. This particular phase is critical in readying the data for machine learning algorithms. Given that many algorithms necessitate input data to fall within particular ranges to achieve optimal functionality, the provided code snippet is a vital component of the data preprocessing phase essential for setting up a machine learning model, particularly those that leverage historical data for predictive purposes, such as recurrent neural networks, RNNs, or long short-term memory LSTM models. To elaborate on the functionality of the code 1, initially, it isolates the training data from a larger dataset that has undergone previous scaling or preprocessing steps. 2. Subsequently, it establishes qutrain and utrain lists to store the input features and corresponding output labels crucial for model training. 3. By utilizing a for loop, it cycles through the trained data, commencing from the 60th element. This approach is integral in cases where the model is trained to forecast a data point based on the 60 preceding data points. 4. During each iteration, it appends the preceding 60 data points features to utrain and the data point slated for prediction label to utrain. 5. Within the loop, an if statement is incorporated to display the utrain and utrain values during the initial iteration. Typically, this step aids in troubleshooting and verifying the accuracy of data preparation. This preparatory procedure proves indispensable as machine learning models, particularly those handling sequential data like time series or text, mandate input features in specific configurations to ensure precise predictions. By structuring the data in this manner, the model can effectively discern patterns and correlations within the historical data, enhancing its predictive capabilities on unseen data. The given code snippet serves to transform the variables qutrain and utrain into numpy arrays. Numpy arrays stand out for their capacity to handle numerical data effectively in Python. Through the conversion of qutrain and utrain into numpy arrays, we unlock the potential to tap into the array operations and broadcasting features of numpy. These capabilities not only streamline processes but also enhance computational speed compared to using standard Python lists. In the realms of machine learning and data processing, converting data into numpy arrays is a widespread strategy to harness the superior performance and functionality that numpy offers. This conversion empowers us to execute diverse mathematical operations efficiently on the data residing in the arrays. This piece of code adjusts the shape of the qutrain array by appending an extra dimension with a size of 1 to it. This practice is common in the realm of machine learning, especially when dealing with sequential data or deep learning architectures that mandate a particular input structure. The numpy library's Reshape function is instrumental in modifying an array's configuration without altering its underlying data. In this instance, the focus is on enhancing the qutrain array by introducing an additional dimension with a size of 1. Following the reshaping process, the console will display the new shape of the qutrain array. This procedure proves vital in cases where a model necessitates input data to be presented in a specific format, such as supplying sequential data to a recurrent neural network RNN or a convolutional neural network CNN. Through this reshaping approach, we guarantee alignment with the anticipated input format of the model being leveraged, consequently enabling the model to accurately handle the data throughout both training and prediction phases. This snippet of code demonstrates the construction of a sequential model using the Keras API along with the TensorFlow backend. The model comprises a series of layers arranged in a specific order to fulfill various functions. 1. Sequential model. This method enables the creation of models layer by layer in a step-by-step manner, ensuring that the layers operate in the sequence in which they are added. 2. Long short-term memory layer, an essential type of recurrent neural network RNN layer tailored for sequence prediction tasks such as time series forecasting. Bilsum layer introduces memory to the network, empowering it to acquire and retain information over extended sequences. Plus 50. Returns construct input shapex train shapecone. 1. This initial LSTM layer incorporates 50 memory units and is configured to return sequences rather than a single outcome. The input shape parameter defines the format of the input data. 50s. Return sequence false. The subsequent LSTM layer features 50 memory units, but this time, the return sequences parameter is set to false, implying that it will provide the output solely at the concluding time step of the sequence. 3. Dense layers. These layers represent fully connected components within the neural network. Dense at 25. This layer is packed with 25 neurons and relies on the default linear activation function. It introduces a fully connected layer to facilitate additional processing within the model. Dense con with just one neuron. This dense layer serves as the output layer, generating a singular continuous value as the final result. In essence, this code segment assembles a sequential model housing two LSTM layers, engineered to comprehend sequential data like time series. It also integrates two dense layers to conduct further operations and deliver the ultimate output. The model's architecture caters specifically to tasks such as time series prediction, emphasizing the essence of recognizing patterns across temporal sequences. This piece of code compiles a neural network model utilizing the atom optimizer and mean-squared error loss function. Let's break down each part. 1. The optimizer atom, short for adaptive moment estimation, is an optimization algorithm prized for its adeptness in handling sparse gradients typical of noisy problems in deep learning tasks. Among the neural network training algorithms, atom is a top preference since it merges the strengths of Ada Grad and RMSE. 2. The loss function mean-squared error for regression challenges. Mean-squared error (MES) is a widely embraced loss function. It computes the mean of the squared discrepancies between predicted and actual values. By diminishing the MES throughout training, the model enhances its predictive accuracy. It is crucial to compile a model prior to training to configure the learning process effectively. When you furnish the compile method with the optimizer and loss function, you are stipulating how the model should adjust its weights during training and how it should assess its performance. In this section of the code, the fit method of a machine learning model is utilized to train the model with the provided training data. To train and utrain, the train denotes the input data utilized to train the model, while utrain signifies the target labels linked to the input data. Setting bath size specifies that the model will update its weights after processing each individual sample in the training data. A technique recognized as stochastic gradient descent with a batch size of 1. Additionally, setting a post 3 indicates the number of iterations the model will perform over the complete training dataset. Upon invoking model fit, the model undergoes adjustments to its internal parameters, specifically the weights, aiming to minimize the variance between the predicted output and the true target values. This refinement procedure involves predicting outcomes through forward propagation, evaluating discrepancies via a loss function, and refining weights through backpropagation. Training a machine learning model plays a crucial role in making precise predictions on novel, unrevealed data. The training phase empowers the model to grasp the underlying patterns and associations within the training data, bolstering its capacity to generalize effectively to unobserved data submissions. Below is a script that readies the testing dataset for a machine learning model. Let's delve into its operations. Firstly, it segregates testing data entries from the SAIL data following the length of the training data. Essentially, it isolates data points beyond the training set to form the testing dataset. Next, it initializes HaTest and UTest, acting as receptacles for the input features and output labels, respectively, of the test dataset. To generate input features for the test dataset, it iterates over a specified range, starting from 60 to encompass the final 60 data points of the training data up to the test data's length. In each loop, a sequence of 60 data points from the test data is appended to the test roster. This sequence moves by one data point per iteration, constructing a sliding window of 60 data points. This code streamlines the testing dataset setup for the machine learning model by organizing input features test and their corresponding output labels UTest. These elements are pivotal for assessing the model's performance on fresh data. By fashioning data point sequences from the test dataset, the model can leverage historical data for predictions and grasp underlying data patterns more effectively. The variable test is transformed into a numpy array through the utilization of the NIP array function from the numpy library. Numpy arrays serve as a robust data structure in Python, enabling streamlined numerical computations and manipulations on arrays with multiple dimensions. It is frequently essential to convert a variable into a numpy array when handling numerical data and executing numerical tasks like computations, transformations, or model predictions. Numpy arrays offer a more efficient and convenient approach to managing numerical data in comparison to conventional Python lists. By making use of numpy arrays, we can harness the extensive functionality furnished by the numpy library, such as element-wise operations, broadcasting, and optimized mathematical functions. This facilitates the process of handling numerical data in Python. The following line of code modifies the test numpy array by expanding its dimensions. Essentially, it appends an additional dimension of size 1 at the conclusion of the array. Reconfiguring data is a typical practice in scenarios involving neural networks or machine learning models that necessitate input data to adhere to a specific structure or configuration. Adding an extra dimension becomes crucial for certain deep learning models to adequately handle the input data. By adjusting the shape of the test array in this manner, It guarantees that the input data aligns with the anticipated format for the model to execute precise predictions or classifications. In this snippet, we are leveraging a machine learning model to generate predictions on a test dataset and subsequently reverse transform those predictions. Allow me to walk you through each phase. 1. Firstly, the line predictions model. Predictist employs the machine learning model referred to as model to forecast outcomes on the test dataset HOTest. It's crucial to note that the model underwent prior training on a distinct dataset and is now being utilized to forecast results based on the features contained in the test dataset. 2. Post obtaining the predictions via the model, the next step involves reversely transforming these predictions through the utilization of a scalar object. Denoted as scalar, this scalar likely played a role in scaling or normalizing the data during the model training phase. And now we are undoing this process to restore the predictions to their original scale. The reverse transformation becomes imperative here as it facilitates the restoration of predictions to their initial scale or representation, enabling straightforward interpretation and comparison against the actual results. The implementation of this code guarantees that the predictions remain meaningful and interpretable within the framework of the initial data characteristics. On the whole, this code assumes a pivotal role in the prediction pipeline by converting scaled or altered predictions back to their primary scale, thereby enhancing comprehension and assessment. This piece of code computes the root mean squared error RMSE comparing the predicted values predictions to the actual values you test. Here's the breakdown of its operation. First off, it calculates the difference between each predicted value and its respective target value to determine the error associated with each prediction. Next, it squares these errors to standardize them positively and computes the average of these squared errors. Ultimately, it calculates the square root of this average to derive the RMSE, which serves as an indicator of the typical discrepancy between the predicted values and the actual values. RMSE acts as a widely used metric for assessing regression models' effectiveness. A smaller RMSE signifies superior model performance by denoting a reduced average variance between predicted and actual values. The deployment of this code enables us to quantify our model's predictive accuracy performance accurately. The following snippet of code adjusts the style of matplotlib plots to feature a dark background theme. By invoking plot style, use dark background, the plots undergo a transformation that results in dark backgrounds complemented by light-colored lines and markers. This alteration can be particularly advantageous for presentations or instances where plots are showcased in environments with low lighting. It serves to enhance clarity, lessen eye fatigue, especially during prolonged visualization scrutiny. In essence, this code snippet serves the purpose of customizing the look of matplotlib plots to adopt a distinct dark theme, offering an alternative visual presentation from the typical light background style. The purpose of this script is to visually display the process of training data, validation data, and predictions generated by a stock price prediction model. Here's what the script accomplishes. 1. Segregation of the dataset into 2 parts. Termed as train and valid, the training dataset is utilized for model training while the validation dataset is employed for verification purposes. 2. The model's predictions are recorded in the predictions column within the validation dataset. 3. Using matplotlib, a graphical plot is generated to exhibit a comparison among the actual stock market opening prices in the training dataset TrainOpen, real opening prices in the validation dataset ValidOpen, and the forecasted opening prices of the stock market valid predictions. 4. The plot is designed with a title, X and Y-axis labels, and unique line colors for each data representation training, validation, and predictions. 5. A plot legend is inserted to differentiate among the training data, validation data, and predictions. 6. The plot image is saved as prediction thing. 7. Eventually, the plot is showcased using pult show, observing the training data, validation data, and model predictions visually aids in evaluating the model's performance, offering insights into its accuracy and areas that could be enhanced. This visual aid is instrumental in assessing the model's predictive capabilities in the realm of stock pricing, serving as a valuable resource for decision-making in stock trading and investment ventures. The code seems to be aimed at retrieving the last 15 elements of a data structure or sequence called valid. It is likely that valid is an array, list, or another kind of collection where identifying the last elements is meaningful. In this snippet, the function or method tail is employed to fetch the most recent 15 elements from the valid dataset. This is a typical operation in programming for accessing the latest data points or records efficiently. This piece of code proves handy when dealing with extensive datasets or sequences, as it enables us to concentrate solely on the relevant subset of information for our ongoing task. By extracting the last 15 elements, we can scrutinize or manage a more recent and smaller portion of the dataset without the need to handle the entire set of data. In essence, this code enhances the efficiency of data processing and analysis by homing in on the most recent section of the data, which could be crucial in specific situations. The task at hand involves implementing a segment of a system that engages in daily stock price forecasting through a machine learning algorithm. Let's break down the process initially. The software acquires historical stock information by utilizing the Yahoo Finance APIs. It retrieves relevant stock details, such as opening prices, based on a specified ticker symbol within a designated time frame. Subsequently, it filters out solely the open stock prices from the retrieved dataset. Further down the line, the program isolates the most recent 60 days worth of stock opening prices and proceeds to standardize the data using a scaling mechanism. Following this, the application arranges the data in a structure expected by the MO model. It transforms the data into a 3D array to conform with the specific input format required by the model. The software then inputs this altered data into the pre-trained MO model to project the following day's stock opening price. Upon acquiring the projection, it reverts the forecasted value to its original scale via the scaling mechanism. Conclusively, it showcases the anticipated opening price for the forthcoming day linked to the designated stock ticker. Employing this code streamlines the procedure of retrieving historical stock data, preprocessing it, delivering it to the MO model for forecasting, and ultimately disclosing the predicted stock price. This streamlining operation enables rapid stock price scrutiny and prognostication, imperative for executing informed trading judgments within financial realms. This script conducts a time series analysis to forecast the opening stock price of a designated ticker symbol for the following day by leveraging past stock prices. Here's a breakdown of its operation. Initially, it accesses historical stock price information utilizing the Yahoo Finance API for a particular ticker symbol, covering the period from January 1, 2012 to May 24, 2020. Subsequently, it isolates the open price from the obtained stock data and selects the most recent 60 days of opening prices from this dataset. Next, it normalizes the most recent 60 days of opening prices via a predefined seller and configures the input data for the machine learning model by reshaping the normalized data. The machine learning model is then deployed to project the opening price of the subsequent day's stocks. Afterwards, the projected price is reconverted back to the original scale, and the anticipated opening price for the following day based on the ticker symbol is printed. Utilizing this code streamlines the process of predicting stock prices using historical data and machine learning models, providing a swift and effective method to gain insights into potential stock price shift.